Around half a century ago, during the Apollo missions, there were a few instances where astronauts were launched off the surface of the moon into lunar orbit at the end of their mission. While impressive, this process is not nearly as challenging as launching a rocket off a different planet, a feat NASA is working toward right now, a part of the Mars sample return mission. During this mission, NASA will launch and send a large lander to the planet, which will receive samples, place them in an onboard rocket, and then attempt to launch it off the surface. This would be the first time ever a rocket was launched on a different planet. This complex process involves ejecting the rocket up into the Martian air before it lights its engines and attempts to escape the planet's atmosphere. As far as progress, just days ago the agency announced new tests and developments of this rocket's first and second stage engines. This milestone brings NASA one step closer to the initial launch and landing of this hardware. Here I'll go more in depth into the recent tests, how exactly this rocket works, what makes this process so difficult, and more. The Mars Ascent Vehicle, or MAV, is a lightweight rocket with the important future job of transporting the sample return container or orbiting sample into Mars orbit as part of NASA and ESA's Mars Sample Return Program. This program stretches across a decade of rover sample collecting, depots, rendezvous, and eventually Mars samples landing on Earth. This specific stage in this complex process is immensely important and would transport the sample tubes containing Martian rock, atmosphere, and loose surface material into orbit around Mars. The rocket, an enclosed sample container, would travel to Mars inside the sample retrieval lander, and would remain on board until loaded with samples and prepped for launch. Once the sample container reaches Mars orbit, ESA's Earth Return Orbiter, or ERO, would capture and store it in a secure containment capsule for safe delivery to Earth. Before this can happen, however, NASA has been working hard to figure out the challenging process of launching a 1,000-pound or 450-kilogram rocket off the planet. Just over a week ago, the team developing MAV conducted successful tests of the first and second stage solid rocket motors needed for the launch. It's important to point out that the MAV launch will be accomplished using two solid rocket motors, SRM-1 and SRM-2. SRM-1 will propel MAV away from the red planet's surface, while SRM-2 will spin MAV's second stage to place the sample container in the correct Mars orbit, allowing the Earth Return Orbiter to find it. In the recent report, the agency was quoted saying, "To test the solid rocket motor designs, the MAV team prepared development motors. This allowed the team to see how the motors would perform and if any adjustments should be made before they are built for the mission." The SRM-2 development motor was tested on March 29, 2023 at the Northrop Grumman facility in Maryland. Then, SRM-1's development motor was tested on April 7th at Edwards Air Force Base in California. SRM-1's test was conducted in a vacuum chamber that was cooled to minus 20 degrees Celsius, or minus 4 degrees Fahrenheit, and allowed the team to also test a supersonic split-line nozzle, part of SRM-1's thrust vector control system. Most gimbaling solid rocket motor nozzles are designed in a way that can't handle the extreme cold MAV will experience, so the Northrop Grumman team had to come up with something that could. A state-of-the-art trapped ball nozzle featuring a supersonic split line, they said. After all the testing and disassembling of the SRM-1 development motor, analysis showed the team's design proved successful. This test demonstrates our nation has the capacity to develop a launch vehicle that can successfully be lightweight enough to get to Mars and robust enough to put a set of samples into orbit and bring back to Earth, said MAV propulsion manager Benjamin Davis at NASA's Marshall Space Flight Center. "The hardware is telling us that our technology is ready to proceed with development," he said. Not only this, but in addition to motor testing, the MAV team recently conducted its preliminary design review, which was a 4-day in-depth review of MAV's overall design. The Mars Ascent Vehicle project manager said MAV passed that review, which means the team can now focus on continuing to improve MAV before its critical design review next summer. The main purpose of MAV is to carry tubes containing Martian rock and soil samples into orbit around Mars, where the return orbiter will then pick them up and send them to Earth. This process, as you can imagine, involves a lot of moving parts, even with just this vehicle alone. Inside the rocket, the orbiting sample, or OS container, will hold up to 30 tubes filled with Martian rock and atmospheric samples for Earth transport. The OS will keep contents at less than about 86 degrees Fahrenheit or 30 degrees Celsius to help preserve the Mars material in its most natural state. Looking at its flight profile, to launch the rocket into the air, the lander will throw the MAV several meters above itself. The front would be tossed a bit harder than the back, causing the rocket to point upward, toward the Martian sky. The rocket's solid propellant first stage would then ignite in midair and the rocket would take off. It's a loft and light technique spearheaded by engineers at NASA's Jet Propulsion Laboratory in Southern California. The MAV will be tossed into the thin Martian air roughly 18 feet or 5.5 meters above the lander that doubles as a launch pad. At that point, the rocket's first stage motor will ignite, said Steve Sides, Senior Program Manager for the Mars Ascent Vehicle Integrated System. Throwing a rocket up and getting it to light has been done before, but never on Mars, said Sides. The vector approach minimizes blowback and interference with the SRL, he explained. Once ignition occurs, the rocket hightails it towards Mars orbit. Ultimately, the MAV gets on the order of about 9,000 miles per hour to reach Mars escape velocity, he said. Specifically, once in the air, the rocket will employ a two-stage burn to reach Mars orbit. The first stage is thrust vector controlled with a nominal burn time of about 75 seconds. The MAV would then coast and separate from the first stage, dropping with it all active control. The second stage is spin stabilized with a nominal burn time of about 20 seconds and is used to inject into Mars orbit, where it would then deploy the orbiting sample container. Both the second stage of the MAV and the OS would remain in Mars orbit. The first stage would fall back to Mars. We've never launched a rocket from Mars, so there's a lot of technology involved here, Sides said. But we're also going to get a lot of science from those Mars samples. Indeed, returning samples from Mars has been on NASA's to-do list for decades. It's hard, but the technology and time to do this is right. We just have to go and do it, he said. I wouldn't put it in the easy category, but I wouldn't put it in the unobtainable category, he added. We have the capability now. As partially mentioned prior, the rocket's second stage burn would use a method called spin stabilization to keep the rocket straight on its journey. NASA highlights that the physics are similar to the act of throwing a football in a spiral motion to keep it flying straight. It allows the rocket to be lighter, avoiding the need for active control all the way to orbit. However, it means it must be carefully balanced. Every so often, after the MAV reaches orbit and releases the orbiting sample container, it will ping its location to let the Earth return orbiter know where it is. The orbiter uses this information to locate and capture the sample container and its valuable cargo. The Earth Return Orbiter, provided by ESA, would be the first interplanetary spacecraft to capture an object in orbit around another planet and make a full round trip to Mars and back. It would also be the biggest ever spacecraft to orbit the Red Planet. The spacecraft would locate, intercept, and capture a volleyball-sized capsule launched from the surface of Mars. The entire campaign would be operated autonomously away from Earth at over 31 million miles or about 50 million kilometers away. Once the orbiter has completed rendezvous, it would perform a maneuver to capture the orbiting sample container within the NASA-provided capture, containment, and return system on board the orbiter, housed at the upper deck of the ERO spacecraft. To do this, ERO would use high-performance cameras to detect the orbiting sample at over 620 miles or 1,000 kilometers distance. Once locked on, it would track it continuously using cameras and LiDARs throughout the rendezvous phase all the way up to capture by the CCRS. The system will sterilize the outer surface of the orbiting sample container and contain it safely within the Earth Entry System, EES, an equally complex process that requires the rocket to succeed. NASA, along with its partners, are in the process of developing a multi-stage plan to return Mars samples to Earth. This involves the first ever rocket launch on another planet with the Mars Ascent Vehicle. We will have to wait and see how it progresses and the impact it has on the space industry. Thank you very much for watching.